All right, let's take a look at the review for the Unit 5B, Chemistry in the Ocean, Learning Targets 10 through 16 practice. So first we need to label these things as a carbon reservoir, a carbon sink, or a carbon source. And so I think what would be best would be to first define each of these. So a carbon reservoir is something that holds a lot of carbon, okay? Stores a lot of carbon. There's lots of examples of things that store a lot of carbon, like the atmosphere, the human race, animals, plants, things like that. Carbon sinks are processes or things that remove carbon dioxide from the atmosphere. And last but not least, a carbon source is a process or thing that adds CO2 to the atmosphere. So a volcano erupting, that is going from the geosphere to the atmosphere, and it's adding a lot of carbon dioxide to the atmosphere. So this would be considered a carbon source. A forest fire, oops, saw the typo here. That is also a carbon source because the trees in the biosphere burning up turn into carbon dioxide in the atmosphere. Trees as a whole are carbon reservoirs, and because they are undergoing photosynthesis, they're also a carbon sink. They're taking carbon dioxide from the atmosphere more than they're putting it back into the atmosphere. And the ocean would also be considered both a carbon reservoir since it stores a lot of carbon, and it's also a carbon sink. And especially after our speaker, you could also make an argument that it's a carbon source because as the ocean heats up, it can't hold as much carbon dioxide. It's not as soluble in warmer water, and so it will go into the atmosphere. All right, now we need to come up with an example of how carbon could move in these ways. So how can carbon move from the biosphere to the atmosphere? We already had an example of a forest fire. We could also use cellular respiration. So that's breathing. So humans, animals, we are moving carbon into the atmosphere. How could something move from the atmosphere to the biosphere? Well, that would be the process of photosynthesis. So plants take in carbon from the atmosphere to add to grow themselves to grow. The geosphere to the atmosphere, we already talked about volcanoes, but you could also say burning fossil fuels. And then how could something go from the atmosphere into the hydrosphere? Well, it can be the ocean sinking CO2 from the atmosphere. All right, speaking of, can you explain what happens when carbon dioxide dissolves and reacts with water? When carbon dioxide reacts with water, it makes carbonic acid, which dissociates into HCO3- bicarbonate, and it releases a hydrogen ion. And then this bicarbonate, although this isn't favored, it can release that other hydrogen as well and turn into carbonate. As the ocean becomes more acidic, this bicarbonate is favored over the carbonate. And eventually, if the ocean becomes even more acidic, then the carbonic acid would be the most favored. But as it stands, this one gets the biggest arrow because it's the more hydrogen ions there are in solution, they're combining with these carbonates, forming the bicarbonate. And that creates a problem for shellfish because now there's this competition because the shellfish, the calcium, wants to find CO3 2 minuses, but instead a lot of them are unfortunately already HCO3 minus, and that doesn't do the calcium any good. So then it can't form the shell because a shell is calcium carbonate. Why does adding CO2 to water lower the pH? Because it increases the H plus concentration. And the higher the concentration of H plus, that means the lower the pH, which means that it's more acidic. Next learning target, I can explain what's meant by chemical equilibrium and predict whether a change will cause the reaction to shift left or right, according to Le Chatelier's principle. All right, so we've got a reaction here, and we can see that it's reversible. It can go both ways. When the forward and reverse rate are equal, then the reaction has reached equilibrium. If we lower the temperature, the reactants, the products, are gonna, the reactants and the reverse reaction, they're gonna try to compensate for that. And so this is gonna cause this reaction to shift left to try to make more heat. Since it got colder, they're like, oh no, we've got to make more. Increasing the pressure, there's a gas on both sides, but there's actually two gases on the right. So this will cause a shift to the left because there's two gases on the right that will collide and react more. If you remove H2, what's going to happen? Well, if we take this out, it's like there's a hole here. It's not there. So the forward reaction is going to speed up to try to replace that H2. So this would be shifts right. And then if we add a surplus of H2, the reverse reaction is going to speed up because they're going to try and get rid of that H2. So this is another shifts left. The diagram below shows a mixture of NO2 gas and N2O4 gas in a 1 liter container at 25 degrees Celsius. The gases are in equilibrium according to this equation. So 2 NO2 gas makes N2O4 gas, and the N2O4 gas also goes backwards and makes the 2 NO2. All right, so at equilibrium, we can see in this picture, there are 1, 2, 3, 4, 5, 6 black dots, and there are only 1, 2, 3 white blobs. And so NO2 is favored, and the equilibrium constant is measured by taking the concentration of the products at equilibrium over the concentration of the reactants. And since the bottom number is larger than the top number, you're dividing by this bigger number. And so the equilibrium constant is going to be bigger than 0, but less than 1. And again, we know that because NO2 is favored, okay? And we know that the equilibrium constant is actually calculated by taking products over reactants. And so if the bottom, oops, this should be NO2, if the bottom number is a bigger number, then it's going to come out to be something between 0 and 1. Identify two properties in each of the three sections of the Venn diagram below. All right, so we know that acids have a pH less than 7. Bases have a pH greater than 7. We know that they're both corrosive. We know that acids acids donate hydrogen ions, while bases accept H plus to form OH minus, or add OH minus to solution. So it's a different ion. Both add ions to solution. Acids taste sour. Bases taste bitter. Bases are slippery. What else? Acids are turn universal warm colors like red, orange, yellow, while bases turn universal cool colors like blue and purple. Acids turn cabbage juice that hot pink. While bases turn cabbage juice green or blue. Trying to think if there's any other big ones that we need to cover here. Let me just make sure. I think we got the main ones. Yeah. All right, label each of the following as an acid or a base based on its formula. First one's tricky, but NH3 actually rips a hydrogen off of HOH, H2O, and it leaves behind an OH minus, so that's a base. H2SO4 would actually dissociate into H+, and sulfate ion, so this is an acid. NaOH would dissociate into Na plus and OH minus, so that would be a base because hydroxide ion. And HCl would dissociate into H plus and Cl minus, so that would be an acid too. According to Bronsted-Lowry theory, bases are substances that can accept a proton from water and leave behind an OH minus. Write an equation showing how the hypochlorite ion, which is the main ingredient in bleach, interacts with water. So we've got OCl minus, and I'm going to write out H2O as HOH. Bases accept a hydrogen, so this will be HOCl plus OH minus. That's how we know it's a base. Which of the theories would correctly identify OCl minus as a base? Only Bronsted-Lowry, because Arrhenius' theory said OH must be in the base's formula. So something like MgOH2. That would definitely be a base according to Arrhenius, but we realized there are other things that should also be considered a base, and so they changed how they defined an acid and a base. All right, let's talk about pH. So if we've got standard notation 0.0001, and that's the hydrogen ion concentration, that's the same as 1 times 10 to the negative fourth, right? And if you're unfamiliar with scientific notation, we got to move the decimal back 4 places and add zeros. This would have a pH of 4 because we learned from our most recent lesson that pH is the same as the positive of the superscript. So since the pH is less than 7, this is an acid. Here, since the pH is 10, this would be a base. And we have to write a lot of zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Because if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes. So going backwards, 1 times 10 to the minus 10th, going back 10 spots gets you there. So it's a very small hydrogen ion concentration, so it makes sense that that would be a base. I laugh. If something's neutral, it's got a pH of 7. This would be 1 times 10 to the minus 7th, and this would be 0.00000001. And that is it.